Yeah, welcome. So today we want to look at the theorem under reanalysis. Okay, in particular, under the sequence of real numbers. The theorem is known as Bolzano-Wierestrass Theorem. Okay, so when we say Bolzano-Wierestrass Theorem, is a theorem that was named after Bolzano and is a co-author Weierstrass. Okay, so this theorem is actually talking about a particular sequence that is bounded, and the information about convergence on that sequence is not known. For example, we have a sequence which is defined in an interval a comma b. Okay, but other than this, there is no information of that the sequence is convergent. Example of such sequence is that if I have a sequence which is defined in this interval, okay, suppose the sequence is not monotone, okay, that is, it will give a kind of terms like when n is 1, okay, this will be -1, okay, when n is 2, this will be 1, when it is 3, it is -1, and this is how it continues. A sequence such as this is defined in the interval -1 and 1. However, this sequence, which has both the maximum and minimum, okay, does not converge. Okay, such sequence of this form is what Bolzano-Wierestrass is coming to address. Okay, that if a sequence is bounded, you have information about the boundedness of the sequence, but whether the sequence later now converge or not, okay, Bolzano says that there exist subsequences, okay, at least one that will be convergent. Okay, so let me come again. Somebody said I should come again. Okay, what Bolzano-Wierestrass theorem come to address, okay, is about a particular sequence or sequences, okay, which are bounded, but no information on the convergence of those sequences. Okay, so in as far as it is bounded, we can deduce some subsequences of that bounded sequence that are convergent. We can deduce some of the subsequences that are convergent. Okay, so Bolzano's, okay, so we'll make the theorem more a kind of a way that it will be more understandable to the viewers. Okay, so let's start by giving a theorem, then how Bolzano and Wierestrass are able to prove this. Okay, so after which we will now deduce some facts from the theorem. So let's start. So it says that every bounded sequence okay, so this is the theorem as short as it is. Okay, very heavy when it comes to discussing the proof. Okay, So it says every bounded sequence converges or not has subsequences that are convergent. That is the law. Okay, so let's now see the proof of this. So how do we prove this? Okay, we'll prove this by first considering a bounded sequence. Okay, and in the bounded sequence, we'll try to deduce some subsequences of that bounded sequence. Okay, after which we will now uh, say that those subsequences are convergent. Okay, so before now, we have discussed a theorem called the sandwich theorem. Okay, so that sandwich theorem will be more useful here. Okay, so when we get there, okay, we'll try to recall the sandwich theorem in order to uh, conclude this theorem. Okay, so let's see the skeletal. Okay, let's see the skeletal proof of this. Suppose we have an interval, and then there is a sequence which is defined, okay, in this interval. Okay, from interval A to B, you have a sequence which is defined there. Okay, so let's say the sequence is xn. Okay, but xn is defined in the interval A to B. Okay, now what Bolzano did is this: he considered the midpoint of this interval. That is a point that when we select it, okay, let's say from here to here will be the same as this. Okay, and this midpoint, okay, is nothing but, the formula is nothing but b minus a naught over 2. Okay, that is the middle point of the interval. Okay, so now pick a path either here or here, okay, depending on the pattern of the proof you want to choose. Okay, suppose we choose some here. Okay, so this new interval, okay, you see that it is embedded in this interval. That is the number, the interval from here to here is embedded in this original interval. Okay, and because of that, you see, let this point be A1 and this let point be B1. Okay, so this is another interval. Okay, we'll consider the midpoint of this. Okay, we'll say let it be M1. Okay, so that the length from here to here is the same thing as this. Okay, we'll choose a path from here to here again. Okay, and find the midpoint. Okay, so the new part here will be called B2, and this point here will be called A2. Okay, so we'll find the midpoint of this again and call it N2. Okay, so we'll continue like that, call this A3, B3. Okay, so we'll continue like that until we can no longer bisect the interval. Okay, at that point, we have reached our limit, and that limit is the point of a convergence. Okay, so that's the concept of proof here. Okay, so what we have just done, okay, let's put it down in a in a narrative way. Okay, so that we can get a meaningful uh, understanding of it. So let's xn be defined at the interval okay. Since you say it is bounded, okay, we are assuming a bounded interval. Okay. Okay, so let us be defined the interval this. Okay, so Let's call the interval A naught, B naught. Okay, so divide. So we say let's divide this interval into two parts. Okay, so that m naught will now be the middle, as we earlier said. Okay, so if m naught is the middle point of the interval, okay, so what we are now saying is that we should let the originally, if this is a just as we have it in the interval. Okay, so the new interval we will form is this. Okay, let me bring this again using this interval. Okay, what I've said is we have this interval from A naught to B naught. Okay, we have defined a sequence there. Okay, and after defining the sequence there, we say the information we know about the sequence is that it is bounded. Okay, but we do not have any information about the convergence of the sequence. Okay, so that said, okay, we now say let n naught be the midpoint here, so that we have divided the interval into 12s. Okay, what we now say now is that we should let this new interval be A1 here, and let this be B1. Okay, so that A1, B1 will be equal to M naught, B naught, as we can see. Okay, A1 is same thing as M naught now, B1 is same thing as this. What we observe here is that this new interval, A1, B1, okay, is completely inside A naught, B naught. Okay, so we observe this. Okay, so now if we now create another interval, okay, so that this become A2 and this point B is B2. Okay, we'll see again that we have also constructed another interval, okay, that will be inside there. Okay, so we'll continue to construct, okay, until we have a nested, okay, nested intervals. Okay, so after we have done that, we can now make some deduction from the formulations. Okay, so let's continue. I'm just using this to illustrate what we have just done here. Okay, so the next thing is to say that M1 be the midpoint of this new interval. Okay, so that we now have the interval A to B2 to be equal to the new interval that we have just. Okay, so we'll stop. Okay, also let M1 be the midpoint of A1, B1, okay, such that okay, so if A1, B1 is the interval and M1 is the midpoint, so as we have said, okay, this will be A2, B2, okay, will be equal to M1, okay, comma B1, okay. So I think we have seen the pattern this way. Okay, we'll now say continue in this manner. Continue in this manner. up to the nth, okay, up to the nth term. Okay, so if you continue bisecting the interval, okay, up to the nth term, okay, up to the finite term, okay, what we observe is this. Okay, so observe that we have deduced subintervals and these some subintervals are of this form, such that the original interval is this, is the A naught, B naught, and what we did after this is to find an interval which is contained there, okay, and the interval is A naught, A1, B1, okay, we also construct another one, okay, that is the A2, B2, okay. What we have done here is that this is A naught, B naught, is a superset of this, okay. So it's a superset, okay, and this continues up to the nth term, an, bn, okay. So this is what we have formulated. So, and now to express this further, it means in each of the interval, okay, this an, bn, we can now call it a kind of okay. We are trying to explain that if you have a subsequence which contains in this interval, then this snk means that when we say Sn1, then Sn1 is an element here. Okay. You can say Sn2 is also an element here. Okay. And we can continue this up to the finite term. Okay. You can continue this up to the finite term. Okay. So what you are seeing essentially is that, okay, as you can see, up to this. So this is what we have at. This is when k is 1, we have this one. Okay, so in summary, so what we are saying in a sense is this. Okay, we are able to formulate subintervals such that if you let each of the interval to be a subsequence of the original sequence, okay, each of them will have this form. Okay, so an less or equal to this. Okay, so further, let's further say in each of the interval, okay, we now see that again, B1, if you want to measure B1 minus A1, this is simply B naught minus A naught divided by 2. Okay. Similarly, if you want to measure B2 minus A2, this is B1 minus A1 divided by 2. And since we have expressed b1 minus a1 as this earlier, okay, we can similarly say we want to express this in terms of this again. So that this will be b naught minus a naught divided by 2 or 4. Okay, so when I say 4, this means 2 squared. Okay, what I've done is to replace b1 minus a1 with this. Since we have b1 minus a1 here, so we are replacing it with all this. So when we do that, this is what we have. Okay, so if you continue this up to the nth term that we have said, okay, also we have b3 minus a3 to be equal to b2 a2 divided by 2, and since we have b2 earlier here, okay, we can replace this so that this will be b naught a naught all over 2 raised to the power of 3. So if you continue this up to k, okay, or up to n, okay, what this means is that this will be b naught minus a naught all over 2 raised to the power of n. Okay, so this is what we have got. Okay, now, but we have said want to continue to obtain the subintervals infinitely, meaning we will not stop here. Okay, we have to extend this infinitely. Okay, so now to do that, what we said is that answer now as n move to infinity, so we want to obtain this as n goes to infinity. So this will be nothing but the limit of b and an. Okay, so we are taking the limit of both sides as n goes to infinity. So the limit of this as n goes to infinity will be b naught a naught everything over 2 raised to the power of n. Okay, so we'll see that b naught minus b naught a naught is fixed. Okay, so since that is fixed, when we apply this limit on this, okay, so this n here becomes infinity, okay, because we say n tends to infinity. Okay, so this will be b naught a naught all over 2 raised to the power of infinity. Okay, so we now see that this denominator will be very big in such a way that since this is fixed, okay, this is nothing but 0. Okay, so it will be nothing but 0. That is a finite number divided by a very big number. So that will be 0. Okay, so what it means is this. Okay, so this implies that the limit, by law of limit, we can split the limit on each of this. So that this will be this. Okay, this is equal to 0. And what this simple means further is this. Okay, we'll transfer this term to this place. So this becomes this. Okay, so it means equality happens. It means the limit of bn is the same time as the limit of an. Okay, so the more we bisect, okay, as n goes to infinity, okay, what we are saying is that the limit of bn, the new terms we have constructed, and that of an will be the same. Okay, and we say each of them is equal to L. Now, since each of them is equal to L, so we will recall that we have also defined an interval of this form, interval that recall we have posted something there that the sequence we have constructed is of this form. Okay, so if you take the limit of this, okay, what we are saying is that if you take the limit of an, the limit of an is L. Okay, and when we take the limit of this, it's also L. Okay, this now takes us back to the sandwich theorem. Okay, which says if you have a sequence which satisfies this inequality, if this is convergent and this is also convergent, compulsorily what is that the middle will also be convergent. Okay, so if you can record that under the sandwich theorem, okay, in one of our physical class, we have discussed that. If this sequence converges and this also converges, if there is no information about this, compulsorily this will also converge to the same point for the two. Okay, so Now say by sandwich theorem. By sandwich theorem, okay, the subsequence okay, so sorry for the cutoff. Okay, so now what we are announcing is that you recall that we have earlier obtained the subsequence of this form, okay, and then uh, by sandwich theorem, the formation we had earlier is that if the limit of this is L, and the limit of this is L, compulsory the limit of this will be L, okay, so that is what we have said, okay, as n goes to infinity, okay. So this now conform with the statement of the theorem that says every bounded sequence, okay, whether converges or not, okay, has subsequences which are convergent, okay. We have generated a subsequence is the SNK, and we are able to see that this SNK converges to L, okay. So a picture Q of this is this. Suppose we have a plane. Let's have a picture Q of what we have discussed. Suppose we have a plane of the interval. Okay. Now let's say the A naught is this, and this B naught is this. Okay. Of course, this is defined on R. Okay. And this is defined on R. Okay. So let's say this is the same A naught and the B naught. Okay. This is under R. This is the B naught. Okay. So let's make some more wider and to okay, B naught. Okay. So we are just trying to represent this on a plane so that we want to see how the true picture look like on a plane. Okay. So though we have considered only single R, okay. So I want to see that this interval is actually the nested type. Okay. So when we find the midpoint, okay, the midpoint is somewhere here. Okay. And then the first midpoint is which is M naught that we have said. So and we say we'll bisect this again so that whatever is there will be under midpoint. Okay, so if you do that on both sides, this is what we get. Okay, if you do the same thing for this, okay, same thing for this. Okay, so the first interval, okay, passes through the point like this. This will be the first plane we get. Okay, so the second plane, okay, that this one will take the midpoint of the second time. Okay, this is what we get. Okay, if we bisect this again, and this is the midpoint of this, so we get this again. Okay, we get this again. We get this again. Okay, so continue. Okay, it will get to a point where this will no longer move again. Okay, when it's no longer move, okay, what we are saying is that this sequence, okay, is now going to a particular point. Okay, and that point there is a L, which will be the limit of that sequence. Okay, so it means if you continue, and so this is just a way of magnifying the interval. Okay, but the interval is not as big as this. Okay, okay, there will be some net here. Okay, that will be very, this will be shrinking as it is going further, it will be shrinking. Okay, all this place will be, okay, there will be a kind of a cluster point, okay, around that, okay, so that this part will be more solid than this part, okay, so that is what the theorem is saying there, and it's known as the Bolzano-Wierestrass theorem. Okay, so that is that on this. So example of this, I think we have given one earlier of okay, just one, a simple one for the matter. Okay, example of a sequence that is bounded from -1 to 1. You can do subsequences, okay, -1, the set of elements -1 is a subsequence of that. And we can see there that that is finite because it's the -1, -1, -1. And similarly, we can bring some terms out from there, which are positive one, positive one, positive one, which is also subsequences. Those two subsequences are convergent. That's where we are going. Okay, so we have a consequence of this theorem, and that theorem is called the theorem of nested interval. Okay, so we deduce that concept from what we have here. Okay, this only tells us that this subsequence converges. Okay, but there is no additional information about that. So let's see. Okay. Okay. What we are saying here is that if these are two sequences, okay, so this sequence is on one side of this. Okay, this sequence is on one side of this, and this other sequence on one side of this. So if this is a one, okay, that is A1, B1. Okay, so we'll say this is this. Okay, in that sequence, we obtain a point of this one. And after obtaining this, if you obtain A to B2, okay, if you take the interval of that, the interval is embedded there. Okay, if you now take A3, n to the 3, when n is 3, okay, you see that the interval of this with this. And this is so as n goes to infinity. Okay, this is so as n goes to infinity. Okay, so this now says that then the infinite intersection of this interval. Okay, this is infinite intersection of this interval. Okay, now as it is going, okay, you see that this is becoming, the interval is becoming nested. Okay, so if you now continue that up to infinity, okay, what is saying is that if you now consider the intersection as n goes to infinity, okay, this says this set is non-empty. Okay, and it is a singleton set. Okay, what we are saying is that if you nested the interval this way and consider the intersection, okay, of this set, okay, to be non-empty, okay, and once is inside the set at the end be a singleton term. Okay, we can now relate this to the theorem we just concluded. Okay, where it says if you obtain a sub-interval of an interval. You do it for the first time, second time, and continue to do that up to infinity. Okay, and okay, we'll later arrive at the point where the refinement will no longer be allowed. Okay, where that point will now be called L. Okay, you see that L, okay, is referred to as a singleton set. Okay, inside this interval. Okay, so the proof of this is straightforward. Okay, from the knowledge of the Bolzano-Wierestrass theorem. Okay, now let's see what is actually saying. Okay, so what this is saying is that we assume all these assumptions. Okay, in the statement of the proof. Okay, I think this is taken now. So let us prove now. Okay, so we now see, suppose the proof now. I want to use the same statement here as for the proof. Say suppose AN are sequences or are two sequences such that this happens. Okay, then once we have something like this, what this means is this. So comma then now to see what the intersection of this set will be. Okay, so when we take a finite intersection such as what we have here, what this simply means is that this means the limit, okay, as n goes to infinity of the set this. Okay, this is what that's the interpretation of the finite intersection. Okay, and this is equal to, when we have a limit like this, as you can see, each of these is depending on n. An is depending on n. Bn is also depending on n. What it means is that this limit operator will act on each of them. Okay, and if it does so, if this is also what it means is that this limit will go straight by law of limit. Okay, in the elementary calculus, we have done that. Okay, this limit will go straight to an because this is depending on n. Okay, and the limit also goes to bn because bn is depending on n. Okay. Okay, so we now see by Bolzano-Wierestrass theorem. Bolzano-Wierestrass theorem says that if we have an interval that is nested like this, if you find the limit of an, I think we just did. Okay, the limit of an, okay, is the same thing as the limit of bn, and each of them has the same limit. Okay, so we'll just say, in one of before we say that, we say by, okay, let's say that we now refer to the Bolzano-Wierestrass theorem. The limit of this is L, and the limit of this is also L. Okay, in bracket. Okay, by Bolzano-Wierestrass. Okay, by Bolzano-Wierestrass theorem. Okay, we have that the limit of this is L, and the limit of this is also L. Okay, since the limit are the same, and this is an interval. Okay, this is nothing but a one point. Okay, as we said in the theorem, that the set is non-empty. As you can see, this is non-empty. Okay, because it has one element. And in addition to the statement, they will say the set will be a singleton set. A singleton set means a set with just one element. Okay, so this is what we have there. Okay, and that's the final. Okay, so assuming we do not know what is Bolzano-Wierestrass theorem, when we get here, we'll subject this to proof just as we have it in the Bolzano-Wierestrass theorem. Okay, so it means every statement here, okay, is valid. That is what we are saying. Okay, so how do we use this in practice? In practice, how do we use this? Okay, in we can refer to a concept under numerical analysis where uh, we use a method called the bisection method to obtain the root of a particular polynomial, a nonlinear polynomial. Okay, so under the bisection method, especially for the case where uh, the method of finding the exact root of a polynomial is not readily available. Okay, we resort to a method called bisection method, one of many that numerical analysis use. Okay, so this method, okay, actually let us dramatize this on the board so that suppose we have a curve which passes through the real line. Okay, the curve is f of x, and of course, this remains the real line we are as we are referring to. Okay, of course, we'll see that this point is the root of this curve. Okay, the point at which it crosses the x-axis. Okay, as we are looking for the solution of this function, we are looking for the root of this. Okay, we'll create an interval such as the one we say, or we stated in the theorem there. Okay, let's say this is A and this is B, or more comfortably, let's use A naught the way it is in the proof of the theorem. Okay, you will observe here that if we compute this under the bisection method says that in order that this function has a root inside it, okay, when we compute uh, f of b naught, and when we compute f of a naught, f of a naught is this, and here will be f of b naught. Okay, when we compute them and we multiply them together, okay, the resulting term here must be negative. Okay, as you can see, if you measure from here to here, okay, you see any term that is there is positive if this is the origin. Okay, so if you compute any term here, you see this is negative. Okay, this is positive, this is negative. Multiply negative multiplied by positive. Okay, you have a negative number. So if this happens, okay, under the bisection method say the root of this curve lies in this interval A naught B naught. Okay, having said that, so the next thing is to now just the same way we do in the theorem. The next thing now is to, since we know that the solution, the root of this lies in the interval this, okay, using this testing, recall that if you are doing this in numerical, you don't need to plot a graph to know that using this concept. Okay, so we'll now say let this m naught be the solution. Okay, be the root of that function. Okay, so if this is the root, we'll now say it's an assumption anyway. Okay, we may pick the midpoint. Okay, and midpoint may not be exactly this point. Okay, if it is not, it means we have to repeat that again. So let's see now. We now say under the bisection method, we say let m naught be the midpoint of this, just the same way we have it in the Bolzano-Wierestrass and the nested interval. Okay, so that you can do it either way. You can say b naught minus a naught divided by 2. Okay, of course, you have a time here come m naught. What I'm now saying is that suppose the alt m naught is now here. Okay, if the m naught after computing it is somewhere here, this is just a grammatical solving. Okay, we do not have values to show for this, but we are assuming everything here. Now, after finding this midpoint, the midpoint lies there. Okay. Again, we now say this new term, let it be M1, and no, sorry, let this be A1, and let this point here be B1. Okay. What we'll now do again is that we'll now say from here to here, we'll find the midpoint of A1, B1. When we find the midpoint of A1, B1, that will fall somewhere here again. Okay. And let that one be M1. Okay. This means we have formulated M1 again, and that will be this divided by this. Okay. And then you see that this M1 is not also this point. What we do is that we check again with this method. Okay. Then we'll find this again. Okay. We'll continue to do that until we are able to meet this point. Okay. You see, in the process of doing that, okay, we have been able to formulate a kind of a nested point around this point, though this is the original point we are looking for. Okay. So we have been able to formulate a kind of a nested interval around it. Okay, because there will be many intervals moving there and there, they're moving there and there until you get to this point, then we stop. Okay, so this point is now the limit, okay, of the nested interval. Okay, so the more we do this, the more we formulate an interval. Okay, do this again, you formulate an interval until you get to this point. Okay, so that is the point the nested interval is referring to. And once we have that point will be just one point, and it is unique. That is the meaning. It is unique. So that is how we make use of the nested interval in applications. Okay, you will recall under the numerical analysis, make use of iterative methods such as the bisection method when the normal approach, when the method of solving the problem exactly, okay, is not readily available. We resolve into method like bisection method. So this course doesn't allow us to talk about the bisection method in details, okay, but for future reading, okay, go and check what is bisection method and how this theorem of nested interval is useful there. Okay. Okay, I think you can stop here for this class. So if you have any question, so let me know on the comment section. Okay, so I will. Okay, sorry, somebody said that is blurry. Okay, maybe I can take one or two questions before the video is blurry. Okay. So question. So if you have any question, let me know so that I can, or you can contact me through your representative. Okay, so we can stop here. Okay, so have a nice day.